All right, today we're going to talk about infinite series and their possible convergence. If they do converge, what do they converge to? And otherwise, if they don't, then what's the divergence? So, an infinite series, or simply a series, is just where you're taking the terms and you're adding them all up. You're taking the terms of the sequence and you're adding them all up. Okay, so this is just showing you some notation for that. The nth partial sum, right? So we're going to denote the series with this or this notation. We'll do an example here in just a second. So as we're studying this, there's really two basic questions. Does the series converge or diverge? If it does converge, then what's its sum? So let's look at some convergent and divergent series here. Some examples, see if we can make some sense of this. So if we let n be 1, right, we would have 1 over 2 to the 1. If we let n be 2, we'd have 1 over 2 squared, so 1/4. If we let n be 3, if we let n be 4, right? So this is our first term, this is our second term, this is our third term, this is our fourth term, and so on. But we're adding them up, right? This is an infinite series. Sequence would have commas between this. This is a series. We're adding these all up. And so if we were to show all these partial sums, so if we had just one term, it would just be the half. If we summed up two terms, we would take the first two terms. There's the first term, there's the second term. So I get 3/4 is the sum of two terms. If I was summing up three terms, I'd have a half plus a fourth plus an eighth. In other words, 7/8. If I'd sum up four terms, or 15/16. So if I summed up, let's generalize this. If I sum up n terms, see how my n, if I go 2 to the 4th and subtract 1, I get that 15, and on the bottom you see how I'd have 2 to the n. And that's actually my explicit formula for the sum of n terms. So for example, a sum of 5 terms would be 2 to the 5th minus 1 over 2 to the 5th. Right, so it'd be 31 over 32. And then I don't have to add them all up, right? I don't have to add up 5 terms there. Well, so then the second question becomes, does the infinite series, right? We're trying to see if the sum of all this, remember this keeps going, it just keeps going to infinity. Does the infinite series converge or not? Well, that's asking, does the sequence of partial sums run it to infinity? And I'll tell you. So the limit as n goes to infinity, of the formula for the sum of n terms, and I just run it to infinity. Now notice this is 2 to the infinity minus 1 over 2 to the infinity, right? So it's infinity over infinity. So I'd have to use L'Hopital's rule, or we could do this algebraically as well. Let's do it algebraically for good practice. I look at my bottom term, I'm going to take everybody divided by that 2 to the n. So I multiply the top by 1 over 2 to the n, multiply the bottom by 1 over 2 to the n. And we get a limit as n goes to infinity of 1 minus 1 over 2 to the n all over 1. Well, as this goes to infinity, I got 1 over 2 to the n. So 1 over this huge number, that goes to 0. So I got 1 minus 0 over 1. So it's 1. Therefore, the series, right, if I add all these up, 1/2 plus 1/4 plus 1/8 plus 1/16 to infinity, series converges, and its sum is 1. All right, let's take a look at this next one. So this series, if I was to write out the partial sums, the sum of one term is 1. Sum of two terms, 1 plus 1. Sum of three terms. Sum of four terms. Dot, dot, dot. So the sum of n terms is just n, right? If I was adding up 5, I get 5. If I add up 6, I get 6, and so on. Right? Pretty easy series here. So then the second question, does the series converge or diverge? Well, the limit as n goes to infinity of sequence. So the limit as n goes to infinity of n, right? Sum of n terms is n. Well, we throw that infinity in, we just get this thing diverging, right? It's just shooting up, it's just getting bigger, bigger, bigger. The more terms I add, the bigger it gets, right? So therefore, the series, diverges. And that's because the sequence of partial sums diverges. Yeah, you can just, yep, therefore it diverges. Yep. Let's take a look at this one now. If I was writing this out, sum of one term, I'd have 1 over 1 times 1 plus 1. So I'd have a half. If I had two terms, I'd have a half plus, now I let n be 2. 1 over 2 times 2 plus 1, so 1 over 6. Now if I add up 3 terms, so I get a half plus a 6. Now I let n be 3. 1 over 3 times 3 plus 1, so 1/12. And so on. So it's that 1/20th. And we get 4/5 on that. You could do it for 5 terms, and you get 5/6. So the sum of n terms, you don't have to use n every time. We could even do k this time. Right? Sum of k terms would be k over k plus 1. And that gives you the sum of k terms. So then the second question, after I do the sequence partial sums, does it converge? Does the series converge, or does the series diverge? So limit k goes to infinity, less of k. So limit k goes to infinity of k over k plus 1. Again, we got L'Hopital's rule, infinity over infinity, but we'll do this algebraically again. Good practice. Divide by k. And so you've got limit k goes to infinity of 1 over 1 plus 1 over k. Well, 1 over k, when I throw that infinity in, that'll go to 0. So I got 1 over 1 plus 0. 1 over 1 plus 0 is just 1. Therefore, since the sequence of partial sums converges, so the series converges, and the sum is 1. So the infinite, that's part of it. Infinite series converges. Infinite series converges, and its sum is 1. All right, let's talk a little bit about telescoping series. If you consider that same series, 1 over n times 1, we showed it, by writing it out and then noticing that its formula was k over k plus 1. There's another way. This is also referred to as a telescoping series. And you would only see that if you do it with partial fractions. So if we were doing this with partial fractions, so we'd have 1 equals a times n plus 1 plus b times n. So 1 equals a plus b n plus a. So 0 equals a plus b, and 1 equals a. So now we know 1 is a. So b ends up being -1. So you can rewrite this as a over n plus b, which is b is -1, so -1 over n plus 1. This is the same thing as the original. And then if you write that out, this will what it look. I won't rewrite it, but it'll look like this, right? So if n is 1, you'd have 1 over 1 over 1 over 1 plus 1. So 1 minus 1/2. So there's your first two right there. 1 minus 1/2. Plus, now you let n be 2. Have 1/2 minus 1/3, and so on, right? Well, if you notice this, when you add them up, -1/2, +1/2. See how that's gone? And then -1/3 plus 1/3, that's gone. Plus -1/4, and the next +4. But what happens is all of those just keep collapsing, if that makes sense. And so you're just left with the very first one, 1, and the very last one in this case, minus k over 1. So this is called a telescoping series. It collapses, if that makes sense, right? Like a telescope, you kind of collapse it, an hourglass collapse type of deal. And so it collapses, all those interior ones just all cancel. You're left in this case with the first and the last. So you're left with the first and the last. So now you run that into infinity. That goes to 0. So you got 1 minus 0, which is 1. So this thing actually, you can show that it's a telescoping series and it converges to 1, right? You had to use partial fractions to see that that was a telescope. That's, again, referred to as a telescoping series. I'm not going to get into the proof of that. You're welcome to read that on your own time. Let's go ahead and write one more out. We'll move on to different types, and then we'll also practice a few more of these telescoping series later in this lecture. But let's go ahead and write this telescoping series out. Let me use partial fractions first. So I have 2 over, and pretend I factor this, 2n minus 1, 2n plus 1. So this can be written as a over 2n minus 1 plus b over 2n plus 1. So I have 2 equaling a, 2n plus 1. So we got 0 equaling 2a plus 2b. And then we have the 2, the constant, being 2 equaling a minus b. So I'm going to use, here's my two formulas. I'm going to go ahead and use elimination. So 2a plus 2b equals 0, and a minus b equals 2. I'm going to go ahead and multiply this bottom one by -2. We get -2a plus 2b equals -4. Top stays the same. So I got 4b is -4, so my b is -1. Now that I know my b is -1, I'll just use either of those originals. 2 equals a minus b, so my a ends up being 1 on that. So what we have is this will become the sum of a was 1 over 2n minus 1 plus b. Well, b is -1 over 2n plus 1. So I rewrote it with partial fraction decomposition. And now I'm going to write the sum of n terms. So I'd have 1 over, so I'm going to let n be 1. So 1 over 2 times 1 minus 1. So 1 over 1 minus 1/3 plus. Now let's let n be 2. So I'm going to add in, let's do the second one. So I've got 1/3 minus 1/5. And then 1/5 minus 1/7. And then let me do it 1 over 2n minus 1, 1 over 2n plus 1. Sorry about that. Not enough room here. Now notice minus 1/3 plus 1/3. Those are going to cancel. Minus 1/5 plus 1/5. Those are going to cancel. Minus 1/7 and then dot dot dot. So that's going to cancel with that one. So in this case, we're left with just the first term and, oops, that's supposed to be a minus right there. That's a minus, sorry about that. Last term in this case. So we want to run that. Limit n goes to infinity of s sub n. So limit as n goes to infinity of 1 minus 1 over 2n plus 1. So this will go to 0. So we just got 1 minus 0, which is 1. Therefore, since the sequence of partial sums converges, the series converges, and its sum is 1. All right, let's look at the first series we looked at was a geometric series. You remember geometric series means I'm multiplying by something each time. 1/2 times 1/2 is 1/4. I'm multiplying by a half each time. I'm multiplying by a half. So this is a geometric series. We know from last time, a geometric series, the explicit formula for a geometric series for the nth term was a to the n equals a1, r to the n minus 1. Well, there's also a formula for the sum of a geometric series. So the sum will be a to the 1, the first term, over 1 minus that common ratio. Right? The common ratio r is what you're multiplying each time to get the next term. Right? So you want to keep that in mind. And the convergence of a geometric series tells you that if the common ratio is less than 1, if the absolute value of the common ratio is less than 1, then the series converges to its sum. And the sum is given by a to the 1 over 1 minus r. Okay? So that's it. For a geometric series, that's your geometric series test. Okay? If the common ratio is bigger than 1, the absolute value of it, then it diverges. So let's look at some here with this geometric series test. So if I was writing this out, I would have, maybe I'll write it this way. This is the same as 3 times a half to the n. So I have 3 times a half to the 0 plus 3, because I got to start at 0 this time instead of 1. Then I'm going to let n be 1. Then I'm going to let n be 2, and so on. So can you see how I got 3 plus 3 halves plus 3 fourths, right? 3 plus 3 halves plus 3 fourths. Anyways, I'm multiplying by a half every time, right? I'm multiplying by a half to get the next term. It's my first term, second term. I'm adding up all these terms, but I'm multiplying by a half every time, right? My common ratio is right there. It's a half. So let me erase some of this. The common ratio is a half. Let me notate that. That's what I'm looking for. So this is a geometric series with common ratio being a half. So then we say, since that's less than 1, common ratio, absolute value of the common ratio is less than 1, by the geometric series test, the series converges. And the sum is, now use the formula, the sum for a geometric series is a to the 1 over 1 minus r. So let's go ahead and solve for the sum. It's the first term, 3 times 1/2 to the 0, so 3 times 1 is just a 3. First term over 1 minus the common ratio. So that ends up giving you 6. So by the geometric series test, since the absolute value of the common ratio is less than 1, it converges, sum is 6. Let's do another one here. This is for n being 0, n being 1, n being 2, n being 3. Can you see how you're multiplying by 3 halves every time? So your common ratio here, this is another geometric series. As I told you, these are all geometric series that we're looking at. And the common ratio here is 3 halves. So then I say, well, by the geometric series test, our r is 3 halves. So the absolute value is greater than or equal to 1. If the common ratio is greater than or equal to 1, then the series diverges. Series diverges. Number 1, note here I'm multiplying by a third every time. And by the way, if you're not sure, you can always take second term over the first term. 1/27 over 1/9 gives you 1/3. And it has to be the same as the third term over the second term. 181 divided by 1/27 is also 1/3. So it has to give you the same thing every time, right? That's how you know you have a geometric series, and you know what your common ratio is if you can't spot it. Let's go ahead and just write the explicit formula for the nth term. Notice I don't have a term given, a formula given. So the nth term is the first term times the common ratio to the n minus 1. Or, you could also clean that up and put it in a different form. But I like it right there. That's my nth term. So this series can be written as n being 1 to infinity of 1/9 times the common ratio to the n minus 1. And now we're going to say, well, by the geometric series test, since r is a third, so in other words, the absolute value of that's less than 1, right? The series converges. And the sum is, let's go ahead and figure it out, a1 over 1 minus r. So it's the first term, which is a 9th, over 1 minus the r. That ends up being 1/9 over 2/3, so 1/6. So series converges and the sum is a 6th. Let's write this one out. We're going to start out with n being 0. So I got -1 to the 0, that's 1. Times 5 over 4 to the 0, that's 1. So 5 over 1, I'll just write a 5. That's for n being 0. Plus, now let's let n be 1. I got -1 to the 1, so that's -1 times 5 is a -5 over 4 to the 1. So -5 fourths. Plug in n being 2, so it'd be -1 squared, so that's +1 over 5. +5 over 4 squared, 16, and so on. So this is a geometric series. Your common ratio, you're multiplying by, so another geometric series, where your common ratio is negative 1/4 here. Multiplying by negative 1/4 each time. So we can use the geometric series test since r is negative 1/4, i.e. the absolute value less than 1. Of course, it's going to be greater than 0 because it's absolute value. The series converges again. And the sum is first term 5, 1 minus the negative 1/4, so I got 5 over 5/4, which is 4. So this will all sum, this infinite series sums up to 4. This next one might be my favorite geometric series. This is a geometric series for a repeating decimal. So, if you think about 0.08 repeated, right? That's 0.08080808, blah, 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 right? Well, if I write that as, let me take 8 hundredths, or 8 over 10 squared. If I take 8 100ths, right, 0.08, and I add in 0.0008, or 8 10,000ths, so 8 over 10 to the 4th, and then I add in 8 over 10 to the 6th, that'd be 8 over a million. You with me on this? And I keep going, right? Well, my first term is 8 over 10 squared. My common ratio I'm multiplying by is 1 over 10 squared each time, right, to get the next term. 1 over 100 is my common ratio. So if I was writing a formula for this, this is a geometric sequence, I'd have 8 over 10 squared times 1/100th, or 1 over 10 squared to the n minus 1. So what we're doing is we're analyzing this geometric infinite series. So does it converge or diverge? Well, by the geometric series test, since r is 1 over 10 squared, 1/100th, so the absolute value is less than 1, greater than 0, then it converges. It does converge. And the sum, so what's the sum? First term over 1 minus r. Well, the first term's the 8 100ths, 8 over 10 squared, 1 minus 1/100th. So I got 8 over 100 over 99 over 100. This is 8 over 99, right? 8 over 99 is 0.0808080808, right? So we just found that it does converge and what its sum is, which is the rational expression for that rational number. Just a little commentary here on the removal of finite number of terms at the beginning of the series. So just note, the convergence of a series is not affected by the removal of a finite number of terms from the beginning of the series. So, for example, these two, if you look at 1/2 to the n, if you start at 0, right, I'd have more terms there than I did if I start at 4 for that one, right? So they differ by just the second one, which is more expansive, right? There's more terms there involved. That has a sum of 2. And so, the first one that starts at 4 would be 2 minus those missing terms that I have, right? But either way, they both converge, and they both have a sum, right? Different sums, but they do both converge. And here's some properties of infinite series if they converge, okay? And let's look at the nth term test for divergence here. So one reason may fail to converge, a series may fail to converge, because terms don't become small, right? So if you have like this n plus 1 over n, see how they just keep 2 plus 3 halves plus 4 thirds, right? It just keeps getting bigger, bigger, bigger. Each term's greater than 1, so the sum of n terms here is going to be greater than n, okay? And so if a series converges, then the limit of the nth term will be 0. And note that this is only telling you if you know the series converges. If the series converges. So you cannot conclude the other way around. You cannot conclude if the limit as n goes to infinity of the nth term is 0, then it converges. You cannot conclude that. You don't know that. This is just saying if you know it converges, then the limit of the nth term is 0. Okay? There's the proof on that. You can read through that if you care about that. But if you have any background in truth tables, if you know if P then Q is true, which is the above here, this is my P and my Q, then not Q is not P. This is called the contrapositive. So in other words, if the limit is not 0, then it must diverge. Then it must not converge, in other words, right? So that's called the contrapositive. This is what's referred to as the nth term test for divergence. So we will use this nth term test. So let's go ahead and use this nth term test. Nth term test for divergence, which again says if the limit z goes to infinity, the nth term, the explicit formula is not 0, then the sequence, the series, right, adding them all up, diverges. So let's look at this first one. Limit n goes to infinity, 2 to the n. See how that'll go 2 to the infinity? That just shoots to infinity. So therefore, right, it's not 0. Right, the limit ended up being infinity here. It's not 0, anything but 0. So it must diverge. So by the nth term test, since limit n goes to infinity, 2 to the n is not 0, right? In this case it was infinity. The series diverges. So this next one here, let's take this limit n goes to infinity of this nth term formula, n factorial over 2n factorial plus 1. Notice this is infinity over infinity right now, so we're going to go ahead and divide everything by that n factorial from the denominator. So we got a limit n goes to infinity of 1 over 1, that's a 2 plus, and notice this is going to 0. In fact, let me write it, 1 over n factorial. As I run this to infinity, this is a huge number, so that goes to 0. So I'm just left with 1 over 2 plus 0. So a half. Therefore, by nth term test, that's the limit as n goes to infinity of n factorial over 2n factorial plus 1 is not 0, right? I got a half on that. Then the series diverges. Again, as long as it's not 0, we can conclude it diverges. Let's do one more of these. Limit n goes to infinity of 1 over n. You see how this goes to 0, right? 1 over a huge number. So it goes to 0. So what can we conclude? Well, since limit n goes to infinity of an equals 0, then remember, we want it to not be 0 to conclude it's divergent. So if it does equal 0, the nth term test does not apply. And you can draw no conclusions about the convergence or divergence. We're not sure of the series. This last series, this 1 over n, this is a very useful series, pops up quite a bit. It's referred to as a harmonic series. So if you're writing it out, you know, if n is 1, I got 1 over 1. If n is 2, I got 1 over 2, and so on, right? 1/3, and so on. Again, a harmonic series. So the question is, and it should be noted, strings in music, strings of the same material, diameter, and tension whose lengths form a harmonic series produce harmonic tones, right? So there's actually application, lots of application for harmonic series in music. If you were looking at this with a table, so this is the sum. If we summed up 10 of these terms, 1 plus a half plus a third plus a fourth, anyways, 10 of those, I would get that number. If I summed up 100, I'd get 5.8. If I summed up 1,000 of these, I'd get 7.48. 10,000. Well, slowly but surely, it is growing. Just very slowly. So the harmonic series does diverge. It just takes forever. It takes a lot of, right? Like we're clear up to 1,000,000 and we're only at a sum of 14. Right? But it is diverging. I'm not going to go through this proof. You're welcome to read through that if you want to. And that's because we're going to revisit harmonic series. Harmonic series are what's referred to as a P series. And we'll get into P series in a different section. Okay? But just know that harmonic series does diverge. It just does so very slowly. All right, let's get back to some more. Let's do some telescoping series, some different telescoping series again with our partial sums of fractions. So let's do our partial fractions first on this one. So some more telescoping series. We got 4 over n plus 2 equals a over n plus b over n plus 2. And so we've got 4 a plus 2 and 4 equals so I got 0 equals a plus b, and I got 4 equals 2a. So I know a must be 2, so if a is 2, looks like b would end up being negative 2. So this becomes a over n, 2 over n plus b, well b is negative 2 over n plus 2. And so if we write out the sum of n terms, so I'd have 2 over 1 minus 2 over 1 plus 2 plus, now I'm going to let n be 2. So I got 2 over 2 minus 2 over 2 plus 2 plus plus. And now notice the minus 2/3, but it skips 1, 2, 3 to there, canceling out. The 2 over 2. 1, 2. Wait, I'm sorry, that 2 over 2 is not canceling. The 2 over 4 cancels. Minus 2 over 4, 1, 2, 3. And then the 2 over 5 would cancel. 1, 2, 3. The 2 over 6 would cancel. 1, 2, 3. And that's why I included this one right here, the term before it, in terms of n. It's because it's skipping, right, the red is skipping a couple before it cancels it again. But it is telescoping. It is a telescoping series here. Erase this. And so the sum of n terms is the 2 plus 2 over 2, so plus the 1, and then minus the 2 over n plus 1 minus the 2 over n plus 2. That's what you're left with. And so does the series converge? Well, the question is, does the sequence of partial sums converge, right? So limit n goes to infinity to this s of n. Does this thing converge or not? Well, this will go to 0, and that'll go to 0, right? I got 2 over a huge number minus 2 over a huge number. So I got 2 plus 1, which is 3. Therefore, by telescoping series test, since the sequence of partial sums converges, then the whole series, right, the original series, converges, and the sum is 3. These are all real good you try it problems. If you guys want to pause the video, it'd be a great time to do it. If you want to check it, here we go. So we got 2 to the 1 over 1 minus 2 to the 1 over 1 plus 1 plus 2 to the 1/2 minus 2 to the 1/3. Notice minus 2 to the 1/2 plus 2 to the 1/2. Those cancel. Minus 2 to the 1/3, and the next one cancels. And then we got minus 2 to the 1/4, and so on. So that one will cancel with that one. We're just left with that first and last. So we got 2 to the 1 minus 2 to the 1 over n plus 1. So then we got to think about, does the sequence of partial sums converge? Well, 1 over infinity plus 1, that's a 0. So I got 2 minus 2 to the 0, or 2 minus 1, which is just 1. So sequence of partial sums converges. By the telescoping series test, then the series converges. And the sum is 1. This next one we got, there, I'll do it over here. Sum of n terms, we got square root of 1 minus the square root of 2. Square root of 2 minus the square root of 3. Square root of 3 minus square root of 4. And so on. That one cancels with that one. Minus, plus. So we got square root of 1 minus square root of n plus 1. So if I say it is the limit of a sequence of partial sums converge or not. Well, this is giving me infinity, so we got 1 minus infinity or negative infinity. So this thing diverges, right? Negative infinity. So therefore, it diverges by the telescoping series test. Notice that one and the next one cancel. So minus sine 3 plus sine 3. Oops, minus sine 4 plus sine n. So you're left with sum of n terms is the sine of 1 minus the sine of n plus 1. So when you're thinking about does the limit of sequence of partial sums converge, got to kind of think about this one analytically here. Sine of 1, of course, is just a value, so that's some number. But this sine of n plus 1, well, if you think about the sine of n, just the sine function, right? It just bounces back and forth between 1 and negative 1, all right? So the sine of n plus 1 is just moving that to the left one, right? But it's still just bouncing the values. The values are just bouncing between negative 1 and 1. So that's diverging, right? It's just bouncing back and forth there. It's never, doesn't have a limit, if you will, right? So therefore, by telescoping series test, this diverges. All right. And that's it. Appreciate you guys taking notes. See you next time.